I'm the director of the Proctor Maple Research Center in Underhill Center, Vermont. And this morning we're going to talk about how microbes affect the maple process and lots of different components of it. It was actually not something we were doing research on, but the Franklin County maple producers asked us to come up for their meeting back in October and said, could you tell us something about how microbes affect sap spoilage? And so we started to look into it. We did a few little experiments and then began working on this presentation, and you know, that took about 10 minutes to really talk about that portion. So we expanded it to include lots of other different aspects of how microbes are important in the maple world. And so we're going to go through some of that. It's a bit lengthy, and we'll try to go through it fairly quickly. But if you have questions, you can ask them as we go along, and I'll try to address them unless there's something that's going to come up later. I also want to point out from the very beginning that a lot of this is work that was done in other places. I'll point that out as we go along. So this isn't entirely research that's been done at the Proctor Center, but really pulls from a lot of different research in different institutions. So today we're going to talk about why do microbes grow in sap, what types of things will grow in sap and syrup, and then we want to talk especially about how it affects the particular issue that we're discussing and methods of controlling microbes to end up with less of an impact. We're going to start with the tree and talk about wounding and compartmentalization, and then sap, the effects of microbes on sap, yield and quality and chemistry a little bit, and all these different aspects, and then move on to syrup and how it affects syrup quality, storage, and different types of properties. Lots and lots of interesting effects that microbes have, and they're all over the place, and so we get lots of different types of things going on. First, we'll talk about the microbe effects on wounding and compartmentalization. You may have heard that term before, but whenever we put a tap hole in a tree, it creates a wound. And the wound response that trees have is somewhat different than what animals have. For animals, you make a wound, they have blood vessels that will move in different types of components that can try to fight any infection as it gets started. Trees don't really have a circulatory system like that, so what they do instead is they produce different metabolic products, mostly phenols, and you may have heard about phenols. Phenols are used as antimicrobial compounds for cleaning in various cases, and the tree will put those antimicrobial substances into the wood area around the tap hole to try to keep the infection from spreading. Call that process walling off or compartmentalization. And what you see from that is the development of this brown wood that's around the tap hole. It's about as wide as the tap hole is and about as deep as the tap hole. It doesn't extend much beyond them in those dimensions, but vertically the stain is much, much longer because that is the way that the vessels are oriented in the tree. The vessels that move the sap through the tree are oriented up and down, so the tree will put those substances in there as a way to prevent any type of bacteria or fungi or yeast from getting in there, spreading throughout the tree and causing disease. So what we end up seeing is this tap hole stain that occurs. One thing that's pretty important is to realize that that area of stain isn't exactly the same as the area that the sap comes from. Certainly sap will, before the stain develops, move through that zone, but it can move from further away or it can move sideways if you have vacuum. So that stain isn't just the simple place that the sap and the sugar is coming from. It's coming from a much, much larger area in the tree. They're two very, very different physiological processes. Turns out maple trees, which is very good for us, are excellent at compartmentalizing wounds. And that goes into the concept of sustainable tapping. You have to realize that the area that is stained, though, is no longer functional from the tree's perspective in terms of moving water or sap through that affected zone. So if you tap into an area of brown wood later on, you're just not going to get a lot of sap because the tree can't move sap through there. It's built that wall around it, so the wall keeps the microorganisms from spreading, but it also keeps sap from moving through there. And it also prevents the tree from ever using that area of wood again to store sugar. Trees store sugar throughout all the wood tissue, and so once it becomes walled off, the tree can't access that area any longer. That stained wood doesn't really turn into rot most of the time, and so it's good for structure, for holding the tree up, but it's not good for the other functions of sap transport or sugar storage. If the tree can't compartmentalize the wound well enough, or fast enough, or due to some high stress reason, or if the microbe is really particularly virulent, very, very strong, and the tree doesn't have any defenses against it, then we can get disease. Yes, I know this isn't a maple tree, it's a beech tree, but this is a type of rot that you'll see on trees out there. And when you have things like this, it means the disease has started to spread within the tree, and this is the external symptom of that, and which may show up at times and maybe never be seen. Even with these types of problems, the tree can live for a very, very long time because it's compartmentalized that small area or even a very, very large area, and it's trying to keep that rot area from spreading within the tree. So even though we have something like this growing on the side of the tree, it may not result in the tree's death, or at least may not result in its death for a very, very long period of time. So what do we want to do in terms of reducing the impacts of wounding that we create with tapping? Well, first of all, we want to follow tapping guidelines. We don't want to put too many holes in the trees. We don't want to tap very small understory trees because they're in a low sugar storage situation anyway because they're not getting enough light. If you keep an eye on your tap hole closure rates, it sort of gives you a good indication of how well the tree is growing. And as long as the tree is growing well, it should be able to compartmentalize those tap holes well and not create an undue amount of stress to the tree. You can keep an eye on the amount of stain that you encounter within tapping. And this is something that we're starting to recommend producers do. When you don't have to do it for every single tap hole, but in sections of your woods that have been treated the same over time, as you drill the tap hole, just keep a look occasionally at what the shavings look like. You'll always have a little bit of bark, and that's going to be a little brown. But the rest of the wood should really look really nice and creamy white. Should be moist but not sopping wet. It should stick together and be firm. So just keep an eye on that. If you start seeing a lot of brown wood when you're tapping, other than the bark, then it means that your tapping intensity or compartmentalization within the tree isn't going well. And when you tap into those stained areas, because sap won't move through them anymore, your yields are going to be very low. So you want to make sure that the amount of sap you're getting out of the tree is high. You want to make sure that the tree is healthy, so just keep an eye on that amount of staining that you're hitting. Now, periodically you're going to hit some, just randomly you're going to hit some, but if you have areas in your woods where they were tapped with 7/16" spouts for a long time, and maybe your grandfather used paraformaldehyde when he was tapping them, because that's what they did back then, and they had like little 12-inch drop lines and 3 or 4 taps per tree, or they hung 6 buckets on that tree, and you're tapping them and you're finding a hard time to get nice white wood, then maybe you should think about some type of practice that would cut back on the amount of staining within the tree, and there are various ways of going about that. The other thing is crop tree management. Rather than cut out everything to a certain basal area, if you focus on thinning around individual trees to encourage strong growth, then as long as the tree is putting on good wood, then you'll have less chance of encountering stained wood. And then the other thing is just reduce unnecessary stresses in your sugar bush, particularly roads. People don't graze animals quite so much anymore in sugar bushes that they used to. But diseases are oftentimes spread by roads. Sap Street disease, other types of diseases very, very often come about through basal area or basal wounds on the tree from skidding out logs or dragging brush through there with your tractor, or from wounds to the roots from tractors or other vehicles going through the woods. So you want to be particularly careful, especially in the spring. That's the most sensitive time. Unfortunately, it's the time of year we have to be out there with our vehicles in the woods. So moving on to microbe effects on spouts and tubing and sap yield. Talk a little bit about this. Dr. Vandenberg is going to speak more on sanitation later this afternoon, so I won't go to it in any great depth. But microbes are one of the things that really can affect your sap yield. Three big factors in getting high sap yields. Having a good tree resource, good healthy trees, excellent vacuum. The higher the vacuum, the more sap you're going to get out of the tree, and then excellent sanitation. You have to have all three of those things to get really good sap yields. So it is worth paying attention to the effects of microbes on these things. And it's because as the tap hole gets more and more infected with microbes during the season, that wound response of the trees, that walling off, happens faster and faster. The more the tree can sort of sense microbes within the tap hole, the faster the walling off process happens. The more walling off you get, the less sap you get. And so the faster it happens, the less sap you're going to end up with. So sap and drop line sanitation becomes really, really important, particularly in the last half of the season. People sort of have this tendency to think trees don't really do too much. They just sit there from year to year, maybe grow a little bit. They actually can respond very, very quickly to microbes within the tree because they don't want to sit there for a year or two and maybe get infected. As soon as they encounter any microbes within their tissues, they want to prevent them from spreading throughout the tree. If we look at the contamination within the tubing, it happens throughout the season. Once you have tubing that's out there for a few years, it's contaminated with lots of different things. This is a study that was done in Canada looking at different types of microbes that occur in the tubing systems over the season. I just want to point out this scale here, sort of going from 0 to 10, is a logarithmic scale. So for every time you jump up on one of these bars, you're not jumping up, you're jumping up by a factor of 10. So you go from 0 to 1, and then from 1, really, this goes to 100, 1,000, 10,000, 100,000. So by the time you get up here, you're up into the millions of microbes per milliliter. And so what this shows is that whenever you get a warm period, then you find microbe populations will jump right up. It cools off again. You get a nice hard freeze. It's going to kill a lot of them. They fall back down again. And then the next warm period, the populations jump right up again, and then they crash again at the next period. But in general, they tend to increase over the season because you have nice sweet sap there for them to grow in. It's getting warmer and warmer. Things are getting more contaminated. But this happens with all different types of microorganisms that we have in the tubing systems, whether it's bacteria or this is a particular type of bacteria that's very common, Pseudomonas, or yeast or moles or fungi, whatever you have. And when you look at the tubing very, very closely, in this case with an electron microscope, this is kind of what you'd see. It's not real pretty. These are the actual microbes themselves. This happens to be a bacterial species. And they form these colonies. And the colonies that form when they start to group together start to put out mucus. And that mucus is really, really sticky. And so it sticks together. It keeps all the bacterial colony together. And what does it do? It prevents it from being washed away. It makes a nice little home for the bacteria to grow. And these are called biofilms. Biofilms are very, very difficult to get rid of. And that's why in the medical field, they don't reuse a lot of tubing. They just throw it away and use brand new sterile tubing. Once a tubing system has been used and had sap run through it, you're going to have different types of microbes in them. You can knock their populations down somewhat, but you're never going to ever get rid of them again unless you take that tubing and autoclave it. And you're not going to do that. Nobody does. There are other ways to actually get rid of this stuff. If you use something like chlorine gas or bromine gas or ozone, we don't do that because that kind of stuff will kill you. So it's not worth killing the microbes and killing the maple producers and killing the trees. So we have to deal with them being there. And they're going to be there regardless of what you do. You can make it cleaner through tubing cleaner, but you're never going to get it as good as it was brand new. So what do we do to reduce the impact of sap yields? Again, Abby's going to talk about this quite a lot more, but the first thing is just make sure you use very, very good spout and tubing sanitation practices. And really, part of that is understanding what type of choices you have to accomplish your sanitation goals, how they affect the yield, how much is it going to cost you, and therefore what are you going to get in net profit. And that's really the way we like to look at it is, you know, what's the maple producer going to put in their pocket at the end of the season, depending upon what approach they actually use. So you're going to want to choose the thing that actually works best in your particular application. In general, replacement strategies tend to work better than tubing cleaning strategies. So, you know, if you put a brand new piece of plastic in there, it's about as clean as it's ever going to get. You can try to clean it, and you can get it pretty close if you work really hard at it, but it's never going to be as good as it was brand new. So Abby will talk about this particular study, looking at the effects of different types of cleaning and replacement on overall sap yield and net profits. But there really has been a lot less work on sap quality and how sap quality coming out of the woods and how that affects your net profit. It's a much, much more difficult question to understand. That's what Abby's going to show you, and I'm not going to show it to you because she's here today talking about it. That's just a quick preview. So what does grow in maple sap? Lots and lots of different things. This is the short list. It tends to be a few things that grow most everywhere. Pseudomonas I mentioned, but there are some other things that are very, very common. Lots of things we'll find here and there in different sugar bushes, and the particular mix of microbes that you have is going to be particular to your sugar bush and your operation. But we tend to find things like bacteria, yeast, fungi, mold, all the good things. But what is actually there is going to vary a lot based upon where you are, what time of the season it is, how warm it is, how clean your system was when you started, how clean it is when we're actually testing it. The growth rates of these things and the reproduction rates really are dependent upon two major factors. You know, we know we have sugar water there, so we can kind of discount that. There's sugar, so there's energy for these microbes to feed on. But what do we have? What are the other types of things we have to look at? Time, how long it's been, and how warm it's been. And so the longer it's been and the warmer it's been, the more contamination of your tubing systems or your sap you're going to have. So when you have microbes feed upon sap, what happens? Why is that a bad thing? I mean, maybe it isn't necessarily bad. It isn't bad always.
You talked some of the residual stuff that you have at the end of the spring,
Right.
that kind of sits in those drop lines and tubing throughout the summer. Are those January cold spells going to kill a lot of that?
Not going to kill all of them. Many of these things form spores. And the spore is a way for them to survive a period of time when the conditions are not good for the vegetative form. So, spores are kind of like seeds. So we have all these things that'll grow, and they're the things that are changing the sap chemistry. But then they'll produce spores in preparation for knowing that the bad times are going to come. And so a cold snap, no, it's not going to kill all of them. It's still going to be either some of the vegetative form that'll live or spores that'll grow. And as soon as the conditions are good again for them to grow, spores will germinate and they'll start to grow again. So you just can't get rid of them. So this is a nice, pretty picture. And anybody know what this is? It's a pretty picture, yeah. It's a pretty picture of sucrose. This is the sucrose molecule. Sucrose is the dominant, by far, the dominant form of sugar that is in sap. And so when we talk about sap and the sugar that we're getting from that, we're really talking about sucrose and sucrose chemistry. And the thing to look at is it's a very, very big sugar. It's a 12 carbon sugar. So each of these little angles on here are sugars. And then these are other things, hydrogen or hydrogen, oxygen that are attached to them. So every one of these little points is a sugar. So there's 12 sugars, 12 carbon molecules in the sucrose molecule itself. It's called a disaccharide because it's made up of two monosaccharides. The monosaccharides are glucose and fructose, and they're just kind of stuck together with another bond. This single bond here sticks together a glucose and a fructose to make sucrose. So sucrose is table sugar. When you dry it all out, what you end up with is this crystalline solid. If it's really pure, it looks white or clear. So it's a really, really interesting sugar. So this is just another couple of ways that we can look at it. The interesting thing about sucrose, and the reason microbes are important will become, I'll tell you about in a few minutes, but the important thing is that sucrose, when you heat it up, it doesn't caramelize until it gets to about 320 degrees. Well, that's above, hopefully it's above the temperature of the syrup in your pans. If that's the temperature of the syrup in your pans, you're probably a rather unhappy sugar maker. It happens every now and then, but that black char is caramelized sugar or burnt sugar. So the other interesting property of sucrose is it's not what we call a reducing sugar. So here's where microbes come in. You get this great big sugar. It's very attractive to microbes because they can get energy from it. How do they get energy from it? They do this thing called hydrolyzing the sugar, which simply means they split it in two. And they're using the energy of the bond from that molecule, and that's what they're capturing, the energy in the bond. And so you can sort of think of this bond here right in the middle as being a rubber band that's holding it together. And when the microbes break it in two or hydrolyze that sugar, they're getting the energy out of that rubber band. That's life. That's how everything deals with it. They break apart sugar. And so they're getting the energy out of this bond. And so they break that into these two monosaccharides, glucose and fructose. And so those types of sugars also can be used by microbes and by different organisms in what's called the Krebs cycle or in something else that we think about, fermentation. Right? Fermentation, it's a good thing when you make a beer. It's not such a good thing when you're making syrup or when you already have syrup. If you have fermentation in your syrup, not particularly good. So, so these types of things happen all the time. But this splitting of sucrose into the two invert sugars, or the glucose or the fructose, we'd think that that would happen with all the sugar. There's plenty of microbes around, but it turns out only about 2% of the sugar, maybe up to about 5% of the sucrose that we start with actually gets broken down at worst. So when we're making that really, really dark black syrup, you maybe only get about 5% of this and 95% of this. When you're making a really, really light syrup, you've got 99 to 100% of this. And it's only later in the season that you're starting to get this because there's more microbes around. But they're still not doing very much. They're still affecting just a very, very small percentage. But that small percentage is really, really important in developing color and flavor. Because invert sugars, glucose and fructose, end up going through a couple of different processes. They go through a process called non-enzymatic browning. So now we start hitting the term browning that we recognize as making a darker grade of syrup. And it's because of that small amount of invert sugar or reducing sugars that's there. So it goes through a couple of different things. Maillard reactions, which are amino acids that are in the sap combined with these types of sugars, and it starts to turn them brown. And then the other type of thing that happens is caramelization, where you have thermal decomposition of sugar. And it turns out glucose and fructose caramelize at much, much, much lower temperatures than sucrose do. And they're still above the boiling point of the syrup, but the thing is we have niter on the pans that builds up a little bit, or little areas in the pan that get a little hotter than the boiling liquid. And so we start to get the sugar getting trapped on the niter, and it caramelizes right there because it heats up above the boiling temperature of the liquid. And when we get that, those sugars, glucose and fructose, caramelize. When they caramelize, what does that mean? They form colors, and they brown, tan and brown, and they form flavor. So that 2 to 5% of these things undergoing Maillard reactions and caramelization are what yields the full range of flavor of maple syrup, just because the microbes did something to eat the sugar and break it down a little bit. So where is this breakdown happening? Well, it turns out Steve Childs at Cornell did some work where he looked at fermentation. So he was looking at the sucrose level at different portions. So coming out of the tree, you had this much sucrose, but once it hit the lateral line, it had gone through the spout and the drop line, it had dropped down to only about 15.55 from 17.3. Not much of a change, but we already know it doesn't take much of a change for browning to occur. So, and then once you hit the main line, it dropped down a little bit more, but most of the fermentation in the whole system was happening from the tree, from once it came out of the tree to the time it got into the lateral line. And what can we do there? Not a lot. You can clean your tubing, but it probably isn't going to help a lot because of these biofilms. On the other side, you look at glucose. We started out with essentially nothing coming out of the tree, no glucose at all. By the time it hit the lateral line, it had jumped way up. By the time it hit the main line, it had jumped up more. So we're getting the buildup of these types of reducing sugars by fermentation from these microbes right in the tubing system. It does continue from there, but the sap that comes out of the tree is essentially sterile. The microbes begin to grow in it and change its chemistry right away. As soon as it comes out of the tree, as soon as it hits tubing that's got any amount of biofilms or microbes growing in it, fermentation begins. Sucrose concentration can drop about 10% in tubing systems that have been contaminated, and the glucose concentrations can go upwards by about 100 times. Within main lines, it only increases about 2 or 3 times. So most of the microbial action is happening right away. So what happens when it hits the sugar house? We think about trying to keep things clean, trying to keep it processed very, very fast. Well, this is a study that Simone Lachance published in the 2008 Maple Digest, where he looked at what happens when you filter. You're trying to do a really good job keeping microbes from affecting your sap quality and syrup quality. So what are we doing? Well, we're filtering once it hits the sugar house. So this is the effect of filtering, and the better it gets, the lower it gets, the better it gets. So down here would be an 80% reduction in the microbial load. And this are different types of filtering. So this is a DE filter. With the DE filter, we got about 40% of the bacteria out. Doesn't sound really good, does it? Turns out DE was the best. If we use a cloth cylinder filter, we got about 25% out. Bag filter, only about 18. Cartridge filter, we didn't get much out at all. If we look at yeast, this is the raw sap. Yep. This was yeast and molds. If you look at yeast and mold, and this paper is available on the internet. If you go to the Maple Digest site, you can look up old papers now. But this is the yeast and molds. It did a little better job. Yeast and molds tend to be a little bigger than bacteria. So we got almost 70% out with a DE filter, getting close to 50% with a cloth filter, bag filter nearly 40%, cartridge filter a little over 20. And if we look at the total number of particles it removed, the best we could do is a DE filter, a little over half of them. Well, half is better than nothing. Cloth cylinder filter, about 30%. The bag filter, about 23%. Cartridge filter, about 10-12%. So, what this tells you is if you're using a particular type of system, having some quality issues, and can move to a different type of system, well, this is the order. DE is best, cloth next, bag, and then cartridge.
On that DE filter, I know that you're using a swimming pool, right?
That's what they use is a pool type filter with diatomaceous earth. Yeah. They also make them as a sand filter, so you different types. The idea is that it's a pressure filter that's using some other type of media to trap the particles as it goes in.
Now, how about like my operation? I do voltage staging of filters.
Yep.
It's filtered off.
Yep.
It gets filtered before the RO and after the RO.
Yep.
Every stage is a difference, or does it stay?
It depends. If your micron size is better than the previous filter that you had in line, then you'll probably cut it back a little bit more. Each time you get lower micron size, you're going to take more and more particles out. But if it's the same micron size, probably not doing a lot. In fact, if you put a cartridge filter in there at the end, which a lot of ROs have, which, that's what we have in our system, you have that cartridge in, and you don't change it regularly, you're probably adding more into it than you're taking away. So you got to change those RO filters frequently, because they do get ugly.
Do you see the microbial load the same as buckets as well too?
Buckets are a whole different story. It turns out that buckets with galvanizing material actually probably have less microbial problems than tubing does in many cases. Not always. If you have brand new tubing, very, very low microbial loads. But buckets, there's less surface area there that's involved than there is in tubing to be contaminated. And then also the galvanizing metal has a slight antimicrobial effect. There are other issues with buckets, maybe, but in some cases the sap quality is actually better in a bucket than it can be in tubing. The work involved is a lot different, so it's it's a balance there. So one thing that's been tried for a long period of time is using UV treatment to reduce the microbial load, and it turns out it can be really, really effective or completely ineffective, depending upon how you do it. This is another study that Steve Childs did where he looked at microbial load. And again, notice this is a logarithmic scale, so this goes from 1 to 10 to 100,000, 10,000. So what he found was before the RO, they had over 10,000. You can only count up to 10,000 with the devices he was using, up to 10,000 microbes per milliliter. That sounds like a lot, doesn't it? Well, it isn't. We've counted up to 250,000 microbes per milliliter. They're really tiny. Nice sweet sap. There's a lot. There can be a lot of them in there at certain times. So before the RO, about here, didn't really change it after the RO with a cartridge filter. In the concentrate tank, it was about 10,000 after it came out of the RO. But then they ran it through a UV filter. And the UV filter that they used was one that was actually made for maple as opposed to made for water. Very, very big difference. Those that are made for water, not particularly effective. Those that are made for maple, they can be really effective, and it can also be ungodly expensive. That's the problem, is they're really, really expensive. There's a company now trying to work on one that is less expensive. We'll see. That's what they're saying. It's going to be cheaper than the other one. Well, you know, even cheaper than the other one still means it's going to be hugely expensive, but we'll see. So they ran it through this system with a flow rate of 1,291 gallons per hour and reduced the microbes by half. Okay, so 10,000 down to 5,700. But if they ran it through slower, they got microbe level down to 200. That's clean. That's really, really clean. But slowing it down even more really didn't have a strong effect. It did reduce it some, but not a lot. So finding the critical flow rate through these types of filters is really important. Too fast has some effect, not a lot. Too slow has some effect, but the slower you go, you're just slowing down your system. You're not making it better. Okay, so this is, again, Steve Child's work. You're looking at glucose concentration with storage. So if, this was really at the end of the season, so fairly contaminated sap. But if it was kept cold, then you can see that the microbial level, or the glucose, he was measuring glucose, didn't really go up that fast as long as you keeping it fairly cold. If you let it stay warm, though, the glucose concentration really started to increase fairly quickly. So what does this tell you? It says keep it cold, process it fast. Time and temperature are not your friend with sap quality. So we did a study very, very similar way where we took sap at about 2% and we split it up so that we had, sorry that you can't read this very well, this is sap at room temperature, sap that we stored in the cold room. We added some sugar to it to bring it up to about 13 bricks, so it would be about like concentrate, kept some at room temperature, some in the cold room, and we measured microbial load, sugar content, and pH to see what would happen in terms of sap quality. This is what we inoculated it with, kind of ugly looking stuff at the, this is an end of season, really milky looking sap. This particular thing is an Aerobacter aerogenes, which is the stuff that makes stringy syrup. This ropey, stringy, crappy, yucky, bad stuff. This particular organism is the same thing that sours milk. It's the same thing that has a lot of effect on properties when you're making cheese. It's a really, really common thing. It's out there, it's everywhere, but the thing it does for us, that we don't want it to do is make stringy, ropey syrup at the end of the season. So this is how we did it. This little device tells us how many microbes there are. This measures sugar content, and then we can measure pH as well. And what we found was, again, the same type of thing, that if you kept it cold, this was time, so 0 hours to 50 hours in the microbial load. If you kept it cold, it didn't grow as many microbes as it did if you kept it warm, whether it was in sap or concentrate. So again, just higher temperatures are bad for microbes, or higher temperatures produce more microbes. The more time you have, the more microbes you get. If we look at sap sugar, really there wasn't a lot of effect except that you are losing a little bit of sugar over time. Not a huge amount, but you're losing a little bit of sucrose over time, and you're converting it into glucose and fructose, a small amount. But if you look at pH, that's another thing. Again, the same type of relationships where the colder you kept it, the slower it happened, whether it was in sap or concentrate. But warmer and longer periods of time meant the sap pH kept dropping and dropping and dropping. So you end up with sap that's really starting to get sour, not real good quality sap. But it's kind of interesting what some of this can lead to. So what are the types of things you want to avoid? You want to avoid concentrate or sap getting warm. One way that people warm up their concentrate that they really don't think about very much is they recirculate. If you have an RO or you're ROing from your sap tank into a concentrate tank and then recirculating it around, every time it goes through that pump, it warms it up. And it gets hotter and hotter and hotter. And the microbes are saying it's getting sweeter and sweeter and sweeter, and it's getting hotter and hotter and hotter. So you basically have a hot tub for microbes. So if you're doing it that way, you're probably going to make darker syrup.
What happens when you take sap right up to 165 degrees to kill them?
Right away? Don't know for sure, but you're going to kill a certain percentage of them, probably a fairly high percentage at 165. But certain things, not everything for sure, are going to live. There are some things that will live above 165, and we're going to get into that when we start talking about syrup and packing syrup. So can we? It'll probably help a lot. It will help a lot.
Oh, I'm talking about pick it up.
Yep.
165,
Yep.
180, let it cool
Yep.
back down.
As long as you can cool it back down again so it doesn't stay at 165. Yeah. Okay, so why is pH important? You think, why is he talking about pH? pH is important because when you make syrup, the syrup goes through a lot of changes. And you may not realize this, except you do understand niter. When you start with sap, it tends to be slightly acidic, and as soon as you start to heat it, it goes really high in pH or alkaline. And it's called the alkaline degradation phase. Anytime sap or boiling sap is above pH 7, there are certain reactions that occur that make the syrup turn dark and form color. And it's called this alkaline degradation phase. So the whole time, in this case, if you're starting out with syrup that's fairly neutral, the whole time it's making syrup, it's getting slightly darker and darker and darker as it goes through. So has anybody ever had the time at the end of the season where you get the sap that you think, boy, that is not the best looking sap, but I'm going to boil it anyway, and you get done and you're like, wow, that is great syrup. It's really light. It looks good. Doesn't really taste particularly good, but it's really light. Anybody ever done that? Maybe light syrup at the end? It's because you're starting out with your pH so low, it never gets up into this range. It jumps way up here, and then it just kind of steadily creeps down. So you never hit the alkaline degradation phase. You don't make color. You don't make much flavor to make it taste good, though. So you end up with light-colored, not-so-good tasting syrup. It's the end of the season. You're probably done or close to being done. So why do you know that this is happening? Because you're making niter at the same time. Anytime you're in this alkaline degradation phase, you're making niter. So that's how you can recognize that it happens. So sap chemistry changes a lot from the time that the sap comes out of the tree till the time that it ends up being syrup. And the changes that occur are in the amount of microbes that are there and in the type of sugar that's there and in other types of changes in the chemistry of the syrup. And all of those types of changes affect basically the quality, the color, and the flavor of the syrup that you end up with. Sometimes you want that darker syrup, though, and you want those strong tastes. So you can sort of manipulate the system. If If you're selling retail syrup, you don't want everything to be perfectly good every time and make just light syrup the whole season. You actually need to make some higher flavored syrup. So by manipulating some of these, you can actually end up with syrup that tastes quite good and is a little darker. So how do we reduce the impacts if we want to make light syrup? Keep things as clean as you can. Use the best filtering you can. You know, maybe at some point add UV to your sap treatment regime if you're having problems. But keep the sap cold and process it as fast as you can. It's not anything new, not rocket science.
Tim, on that ugly syrup base and stuff in the season, you can make an awful lot of that during the season.
Sure.
If the base, and usually we're down at the base of 4 pH.
Yep.
If we mix previous permeate that's probably got a pH of 7, some number,
Yep.
in with that raw sap, and brought that pH up slightly, yeah, we're going to take it back up with an
Yeah.
RO.
Yeah.
I mean, once we take that back out, it's sure
Yeah.
it's going to be that back at the 4
Okay.
pH.
So here's the problem with that. You're starting with sap at pH 4, and I've mentioned logarithmic scale a few times. pH is a logarithmic scale, so going from 7 to 6 is one step. 6 to 5 means you've gone up 10 times in the amount of hydrogen that's there to make it acidic. Down to 4, you've gone another 10 times. The permeate is right around 7. So if you add, you'd sort of think you add a 4 and a 7, you're going to come out somewhere in between. No, you aren't. You're going to come out somewhere way, way closer to 4, maybe like 4.2. So you got to add a huge amount of permeate to get it to come up. And that's a lot of work. It's a lot of work. You have to RO it again and start the process all over. It might work, but it's a lot of work to do.
I mean, pretty common. You can make 10% of your season.
Yeah.
Of that kind of
Sure.
stuff, and it's like,
Yeah.
do it.
Yeah, and that's a, you know, it's a tough thing to do.
Done on to try to bring that kind of syrup back up to maple grade?
Usually, no, there's not a lot of research being done right now. Are there ways to do it? Yes. Are there easy ways to do it? No. And so I think the packers, if you're selling in bulk, would just prefer to see you stop at that point. And you know, with syrup at $2 a pound for 2016, I don't know the prices. I am not setting the prices. I don't have anything to do with it. But they're probably going to be a little over $2 a pound, given the Canadian dollar. Is it worth? And that's for good syrup. So for poor quality syrup, yeah, is it worth making it? It's up to you.
Is the syrup great when it's metabolism? Is that related to microbial?
No. Nope. Metabolism is a particular off flavor in syrup that can occur particularly early in the season when you make really nice looking light syrup and it tastes horrible. And sometimes it can taste just a little bit horrible, and sometimes it can taste a lot horrible. And different people have different abilities to distinguish that flavor. So, you know, just because you can't taste it doesn't mean somebody else won't taste it and say, yuck, that stuff is terrible. That is due to a particular compound in the sap that comes from the tree. It's an amino acid compound that when boiled, with all these reactions going on, produces something called 2,4-dimethylpyrazine. It sounds really, really scary, but it's just a naturally occurring compound. When you brown your steak on the grill, you're making 2,4-dimethylpyrazine. Steak tastes with that in it, tastes great. Maple syrup with that taste in it tastes horrible. And there's really, unfortunately, not a lot you can do. We have some papers on our website about it, and I'd refer you to those. Ooh, boy.
Do different microbes metabolize sucrose to glucose and invert sugar at different rates, or is it, or do they have different impacts on quality?
Slightly, but they also have different temperature peaks that are optimal for them. So some of them will grow much better at cold temperatures than others will. Others will grow much better at warm temperatures than they will. So yes.
Last year, sugar made pretty nice syrup.
Yep.
It went
Yep.
taste back to what
Yep. Yep. Yep.
kind of trying to determine
It's kind of disappointing that you made that really nice looking syrup and it just doesn't taste so good. Yep.
We did apply to the reduction in the amount of sugar over 48 hours.
Right.
And it didn't look very significant, but in practice or in volume, does that become significant?
It can, but only after a long period of time. The more significant thing that's happening is that we're converting the sugar from one form, sucrose, to these invert sugars. That's probably a much, much higher significance economically to producers than the small loss in total sugar due to microbes. I'm going to plow ahead a little bit and we'll see where we end up. So microbe effects on syrup. So we can have a lot of effects of microbes in the tree, in the sap. They can also affect us in the syrup. What type of things do we have? We have syrup darkening that occurs. A lot of that's due to oxidation, oxygen getting through your jugs or into your barrels that can cause darkening. But some of it can be due to microbes as well. We can get an increase in the intensity of this caramel flavor, which is a little different than the maple flavor. Changes in syrup viscosity. We know what that one is again, ropey syrup. And the ability to filter it can change, especially at the end of the season. And then the addition of different types of flavor defects like ferment or burnt sugar, depending upon how the processing goes, can all affect syrup flavor. So this is a study that was done in Quebec as well, where they just took sap and they added 2 different microorganisms separately. They added this Pseudomonas, I mentioned, fluorescens, or they added this Machia. And what they looked at, both in the laboratory and whether producers were making it, was the odor of, or the flavor of different types of flavor compounds. So for things that they added this Pseudomonas to, it increased the odor of vanilla. And it increased the flavor of vanilla and the odor of maple. So just having that particular microorganism resulted in differences in the types of flavors we were getting out of the maple syrup. So the same type of thing for the maple flavor with this particular microorganism. So, we think about that list I showed you, the short list of all these different microorganisms. All of them are probably having some influence on the total flavor that we get out of maple syrup. And that's why, your maple syrup tastes different than yours does, and yours does, and it's all this mix of different things, as well as the way you're processing it, that are affecting your flavor of the syrup. And you may not really be able to tell from time to time, but it really is one of the things that goes into making your syrup more different than somebody else's syrup, is all of this. So the bedrock geology, the soils, the trees, and the microbes all go hand in hand. And it shouldn't be surprising. Cheeses, lots of other types of things have different microbes that cause different types of flavors. We have that in maple syrup too.
I've noticed in some places, people that have sugar bushes that are in low wet,
Yep.
have a tendency to make a darker green syrup.
They can. I'm not sure exactly why that is all the time. There could be a lot of different things affecting it. Yeah. Red maple being one of them. Yeah. Yeah. The other type of thing that we see with maple syrup is the change due to that microorganism, like I said before, where you end up with ropey sap or ropey syrup. You just can't filter it, and it's caused by this particular spoilage microorganism. At that point, it's probably worth stopping. Or if you get this kind of mid-season, which happens at times, you just have to clean everything extremely well. Get it as clean as you can, all your processing equipment, and start over and hope you don't get it again. Because oftentimes, if you have a problem with this, you'll keep getting it again and again and again until you finally figure out where you're getting the contamination from. And then the other thing is a project that Kathy Hopkins is doing at the University of Maine, which she just kind of calls what's that growing in my syrup. And a lot of people we've talked to over the years never have any type of contamination problem until they start packing glass. So think about that for a minute. Sometimes it's actually true, though, because it turns out glass is cold when you put the syrup in it, and it cools the syrup down below the temperature where you're actually killing a lot of things in there. So you actually have two things going on. Well, one, now you can see it, so if you did have something, then you know you have a problem. But the second is that the glass is cold, and you're packing these small bottles, a little bit of syrup in a really heavy, thermally inert type of glass, and it's just not hot enough to kill the stuff that's going in, because it's always got stuff in it. It's always got something in it. The point is to try to keep it from growing. And the reason it doesn't grow so well in maple syrup is due to water activity. And the water activity is the property that refers to the unbound water in maple. And if there's unbound water, it means things can grow in it. And different types of things can't survive with a water activity less than 0.91. But some things can survive when it's less than that. Maple syrup is about 0.86 to 0.88, so not a lot of things will grow in it, but sometimes a few things can. So Kathy has taken these samples that people have given her with stuff growing in them and tried to find out what's there. She's found so far 74 different things that she's been able to grow. Most of them have somewhere between 1 and 4 different types of fungi growing in the same sample. And they all tend to be fungi. Only one sample had bacteria. We actually had one time that had something called a water mold growing in it. So you know that black stuff that builds up around the bung on the drum? That's probably water mold. Tends not to grow in syrup very well, but it can. So the things that she did find tend to be Penicillium, Aspergillus, and Wallinia. Some samples had more than one type of thing. So what, this is a number of genera or types of fungus that are found in maple syrup. So what is this? Why is this really that important? Well, everybody knows what penicillium is, right? Aspergillus is another thing. These types of things can produce what are called mycotoxins. So they produce penicillin. Penicillin is an antibiotic. It means they try to keep other things from growing. So turns out they can't grow very much of that stuff, particularly if the syrup is packed at the right temperature. But she is trying to find out how much of these types of things can actually grow in maple syrup if it's not done properly. So how is the maple syrup getting contaminated? Well, fortunately, sap can't live through extended boiling, so when it comes out of your draw-off, syrup is sterile. So contamination is occurring somewhere between your draw-off and getting it in the bottle. The temperature conditions are really important, particularly during bottling, and so she's looking at different practices to decrease contamination. So this is in temperature degrees C, but 75 degrees C is 167, 82 degrees C is 180. So you can see is that the number of colonies drops off the hotter it gets. So this is about your 165 right here. So a few things can just barely make it to there. You get up above there, and at least penicillin, you've killed it. Another type, same type of thing. It can grow right up to about 167, 170. Once you get up above that, you've killed it. So this is the temperature required to kill those things. So we're right sort of at 180 degrees, right at the edge for some of these things. So we want to make sure when we pack the syrup, when it gets into the bottle, and until you put that screw cap on, is at least 180 degrees. Not that it went in the bottle at 180, but the bottle, the whole thing, gets to be 180 degrees to kill everything that's in there. So how do we do that? You're never going to get rid of everything, but keep the packing area clean. Keep it as clean as you possibly can. Only use new clean bottles. Make sure your syrup is at the proper density so the water activity is too low for things to grow. Check your bottles, toss out moldy syrup, and especially if you're using glass bottles, preheating can help. But the other thing is tell your customers to refrigerate the syrup after they open it. A lot of times they won't. They'll just keep it somewhere on the shelf. That's when things will start to grow. It's warm, and you can get condensation that happens up on the cap, and it'll start to grow right at the very top. So microbes do a lot of different things in syrup. One more minute. Does anybody make candy or cream? So here's the other kind of neat thing. Invert sugar is what affects crystallization. And Steve Childs has a whole confectionery workbook that's available to talk about how maple producers can manipulate crystallization of maple products to make the right type of products you have. And it largely comes down to the level of invert sugar you have. Because invert sugar, you remember that great big sucrose molecule? That one will crystallize really, really well. The higher the invert level, you get to a point where it just won't crystallize well. Only with 2 to 5% in there, it just will not crystallize. Anybody like cherry chocolates? You know how they make those? They take sugar, white sugar, they add the enzyme called invertase, the thing that splits that sugar into two. So they make a lump of sugar, ball of sugar with a cherry in the center. They add the invertase into it, and then they cover it with chocolate. So it starts out as a solid sugar ball. And over time, the enzyme breaks that sugar down into invert sugar, and it liquefies. And so you end up with, they don't squirt it inside chocolate. They start with a solid lump of sugar. And so it's just confectioners and maple producers can manipulate the different properties of crystallization based upon the invert level. And that's a really key thing in confections. So invert level microbes are really key in that as well. So what do we do? In general, we want to use really good sanitation practices throughout the entire process of maple. But especially at the end, you've killed everything after it's been in your sap. You've made whatever syrup you're going to make. But the key thing at the very end, make sure you keep it from being contaminated so that your customers don't get any ugly surprises at the end. Nobody likes that. Nobody's happy about it. But we can utilize microbes and what they're doing sometimes to help us. But if we know more about them, then we can keep them from hurting us for certain. So, thank you.